Hello everyone, today we're going to learn about a new chapter. So before we continue to our new chapter, I want to recap from our previous chapter, which is diode, that we have learned about PN junction. I hope you still remember the PN junction. Remember the holes, the free electrons, and also the depletion region. Remember? Right? So you also learn about the IV characteristics of the diode, the temperature effects. Also, we have learned about the ideal and practical diode. Also, we have learned about Zener diode and also the circuit analysis by using mathematical approach and also graphical approach. Right. Alright class, so we're going to learn about a new device which is called as transistor. So actually there are two basic types of transistor, which are bipolar junction transistor or BJT, and also another one is field effect transistor or FET. So these two types of transistor we're going to learn in two chapters, which are chapter 3 and also chapter 4. Okay, first of all, we're going to learn about the bipolar junction transistor, or known as BJT. There will be 4 parts for this chapter. The first part is the basic operation of the BJT. The second part is how we're going to do the DC analysis when we use the BJT inside our circuit. The third part is how we're going to do the AC analysis when we use the BJT into our circuit. And the last part is the frequency response, or the analysis at the low and high frequencies for only one configuration of the BJT, which is CE, right, and also the baud plot. BJT, or the name bipolar junction transistor, the name bipolar refers to the polarities that the BJT have. So for one BJT, they have two polarities, which refer to the holes and also the electrons as the carriers inside its structure. Okay, so there are two broad areas that use BJT. First one is as an amplifier, and the second one is as electronic switch. For this class, we will focus on the linear amplifier and also the BJT as a current-oriented amplifier or current gain. You will be familiar with the symbol beta here. So beta is equals to IC over IB. So beta is the current gain, and it is equals to IC is the I refer to the current at the collector part. This one is C, collector part, and will divide with IB. B is at the base part. Okay, so what is collector, what is base? We're going to learn it after this. Alright class, do you remember in diode you have P and also N type of material, right? So here when you have diode, you have P and N type which is put together, and here it will create a depletion region. Okay, and now for transistor, you will have 3-dope semiconductor, so you will have two depletion region. If you can see inside the slide, you can see here you have one and also you have another one. So these two is the depletion region. So if you have two N type of material that sandwich in between P type of material, right, like this, or I draw it over here. Okay, so here is NPN type of BJT, right? So if you have PN junction, the normal PN junction like a diode, and then if you have another P material that sandwich the N type at the middle, right? So here it create a depletion region over here. Okay, so this is PNP type of the BJT. Okay, so if you can see here, the NPN type or PNP type, right, there will be three terminal, right? So the terminal is called as collector, base, and also emitter, right? So if you have NPN, you will have collector, base, and also emitter. All same, if you have PNP type of BJT, you will have C, collector, and then you have base, and also the E, emitter, right? So what is the function of these three terminal, right? So here, if you read this one, the emitter send the carriers into the base region and then send to the collector. So if you have the emitter, like this one, this is the emitter part, alright? So the emitter will send the carrier. The carrier means if this is n-type, it will have more free electrons or more holes. If you remember in diode, for n-type, you have more free electrons compared to holes, right? So if p-type, you have more holes compared to free electron. So if the emitter part is the n-type, so here it means that it sends the carriers. So the carrier would refer to the free electron. Okay, so the free electrons is emit from the emit to the base and also to the collector. Okay, and also at the base region or the base terminal, this one is as the control region. So this one, if you can see here, the size is very small compared to emitter part and also collector part. This indicates that the size of the base terminal is very, very small. So it just to control the emitter, the carriers inside the emitter to flow to the collector. So it's just a controller, right? So let's see why the base is how the base became the controller for the BJT. From the previous slide, we have learned that there are two types of BJT, which are NPN type and also PNP type. So NPN have two N regions separated by a P region. So 2N and 1P. Okay. So for PNP, it has 2P region and also 1N region. Okay, you know that if you want to draw NPN transistor, you draw 2N region and at the middle is the P region, or this one is N type, and then you have P type and also N type. So this is NPN transistor. So PNP has two P and only one N type region, right? So how you want to draw the symbol for the transistor is just draw as inside this slide. You draw a circle with 3 terminal, or this is the current flow for the C, the collector part. So this is the base part and also the emitter part. Okay, so here is at the emitter part, how you want to draw the arrow for the transistor. So if emitter is n-type, right? If emitter is n-type, you remember n is more free electrons, or majority carrier is the free electrons. Okay, so the arrow is from the positive to negative. So the arrow is going downwards to the emitter. Okay, so for the PNP type of transistor, the arrow from the emitter to base. Okay, it is different compared to NPN because here you have from P to N, but for PNP you have from P to N, which is P is at the emitter part and the base is N type. So the arrow will showing to the base. Okay, that's why you see here the arrow is going to the base, and for NPN your arrow is going to the emitter. Okay, so make sure the arrow is at the emitter. Either it goes to the emitter or goes out from the emitter, right? Okay, this figure showing the doping level of a transistor. So you remember you have emitter part, you have base, and also a collector. So emitter part, as you can see inside the figure, has a lot of negative symbols or free electrons. Okay, but at the collector part, it has less free electrons compared to the emitter part. Okay, this image is showing that the emitter part is heavily doped, right? But the collector part is moderately doped. Okay, so if this has more free electrons at the emitter and collector, you know that this is the NPN type of transistor. Okay, and then you can see here at the base is only small, and also the numbers of positively charged of the holes, right, is only 2 compared to here you have 3. So this one is very lightly doped. Okay, so for the collector part, why it has a larger space, but it is moderately doped compared to the emitter. So if you can see here, the collector is to collect the carrier. So that means the free electrons from the emitter part, okay, it will be collected at the collector part. So the emitter will emit the charge, okay, and then the collector will collect the charge, right? Okay, for BJT operations, in this class we're going to learn about the BJT as amplifier. So we're going to learn the BJT operations in the forward active only. Okay, however, for the BJT as a switch, we can use it in saturation region and also the cut-off region, so that it can create a closed switch and also open switch. So here, actually you need to have 2 BJT to create the gate, not the house gate, but the digital gate, right? The OR gate or any gates that related to digital circuits. Okay, when you see a transistor symbol inside a circuit, try to find the arrow. Okay, so at the arrow is the emitter. So here is, this is base, and another part is the collector. Same with this one. Find the arrow. So the arrow is over here. So the arrow shows from emitter to the base, and another terminal is the collector, or C. Okay, so for this one, because the arrow is going from B to E, so you know that this is N-type. Okay, so this is P-type, right? So the collector is the N-type. So for another circuit here, the arrow for the E is from E to B. So from E to B, so it means that the E emitter is P-type, and the base is N-type, right? That's why the arrow is going from emitter to the base. Okay, so how you want to create the BJT as forward active operating mode, right? If you have a diode, if you want to create a forward bias of your diode, you remember? If you have P and then you have N, right, for the diode. So if you want to create a forward bias, you put positive terminal of your battery to the P-type, and then the negative to the N-type. So here you can create a forward bias. So here, if you see your BE junction, This one, the P is connected to positive terminal, right? This is positive. And N type over here at the emitter is connected to negative terminal of the battery. So this one create a forward bias. Okay. And then at another part of your transistor, you have from N to N. So how you want to put the battery? Because this one is N, collector is N type, and emitter also N type. Okay, so just the easiest way is because you know that this emitter, you just see your emitter. Okay, so your emitter must be connected to the source. Alright, so you don't see the collector even though the collector is also N type, but you refer to your emitter, what type of the material is your emitter, and then the emitter will be the reference for you. So here emitter is N type, so N will be connected to negative terminal. Okay, so here you just connect your positive terminal of the battery to your collector, right? And also for PNP transistor, okay, you see your emitter part. Okay, so your emitter is P type, so you must connect your P type to the P source. So another source of the battery, you connect to the N type or the base. Okay, so what happened to the collector part? So collector also P type, but you refer to your emitter is P type. Okay, so your emitter P type, you connect to the P type of the source, right? And then the negative part you connect to your collector. So this is how you want to create your BJT to operate in the forward active operation, right? Okay, if you want to connect your transistor in a different way so that you can have different type of amplifying factor, okay, what you can do is first, okay, example here I take a common emitter. So common mean grounding. Okay, so common emitter means at the emitter part is ground. Okay, so emitter you put ground. So if common emitter means the emitter is ground, so your P and N is giving the you put the bias to your base and also to your collector. So how you want to determine your biasing for your base and collector? Okay, so you refer to your because the ground is emitter part, so you can logically think that the base and emitter is connected to each other. Okay, but how you want to put your battery or your bias? So here you know that the P type is P is positive, so in order for you to make it always forward bias, you can just connect your base to the positive terminal. Okay, so you know that your base is positive, so you connect your base to the positive side of the battery, right? So another part is negative. You know that negative is connected to the ground, which is connected to the emitter because the name is common emitter. So what happened to your collector? How you want to put the biasing to your collector? So since your emitter is N type, okay, if you remember I've told in the previous slide that you see your emitter part. Okay, so if your emitter is N type, you connect it to the negative source, right? So your collector will be connected to the positive source. Okay, so you will have this kind of configuration. Okay. Meanwhile, for PNP type transistor, if you want to have a common emitter as well, so here is your emitter. Okay, so you have ground over here. So how you want to put biasing to your base and also to your collector. So you see your base is N-type, so you connect it to the negative source. Okay, so your emitter is P-type, so you connect it to positive. Even though this is a common emitter, but how you want to put the biasing, you refer to the emitter type. So emitter is P-type, so you connect it to positive. Same with another terminal over here, so the collector and also the emitter. So emitter is P-type, so you connect your P-type emitter with the positive side of your source, and then the collector will connect it at the negative source. Okay, then you have common collector. So the common is collector. Right, so the collector you have a common. Okay, if you remember, I've told you, if you want to put the biasing, you always refer to your emitter. Okay, so if your emitter is N-type, you connect it to the negative side, negative bias, negative source. Okay, and then you all know here that your collector is actually connected to the positive, and then your base. Okay, for base terminal you is P-type material, so P-type you connect to the positive bias. Okay, so here you have negative to collector. Same concept for PNP transistor common collector. Here you have common collector, so you find your emitter. So emitter is P-type, that means your emitter must be connected to positive terminal of the battery source, right? And then your collector is connected to the negative, and then your base is N-type. N-type is negative, so you connect it to negative source. Then on the side positive is connected to collector. The last one is common base. So the base is connected to the ground. Okay, so how you want to determine the biasing for your emitter and also collector? Your base is already grounded. Okay, so first of all, you see the emitter part. So emitter part is N type of material, so N must be connected to negative. Okay, if emitter connected to negative, your collector must connected to positive. Remember, it's always vice versa for your emitter and collector. You see here, this emitter connected to negative and this one connected to positive. Okay, so from here, from this figure, you can see here that the emitter is connected to the negative source and the collector is connected to the positive source. Okay, so you just put your battery, here is the positive, and another battery, this one is negative. Okay, and then another one is PNP common base. So you can see your base is connected to ground. Okay, then find your emitter part. This is your emitter. So your emitter here is P-type. So you must connect it to positive side. Okay. Then another part is collector. Collector must always be different from emitter to ensure the current flow in only one direction. So C or collector is connected to negative, right? Okay, if you remember, when you want to do the biasing for your transistor, you have B and E. You connect to, for example, here I want to make a common emitter. Okay, and then so for the base terminal is P type, so you connect to the positive. Emitter part is connected to the ground, so you put negative. And then for the collector and emitter, the biasing, emitter is, you refer your emitter. So emitter is N type, you connect to the negative. So collector is positive. Okay, so from here you can see that the current flow, usually you just see from the positive of your battery to the negative. So from the positive you have the current flow into your collector part is labeled as IC. Okay, then going to the ground is IE. Right, so here you have from the positive terminal over here, the current flow from the positive to the negative. Okay, and so same for the base and emitter. From the base is positive, so here you have IB. Okay, and then you have IE, right? So that's why you need to really ensure that your biasing for your transistor is correct. Okay, so here you have if your transistor is labeled into the symbols, okay, so this is the symbol. Okay, and then you have your IC, okay, IC, IE, and also IB, right? Okay, so you know that your transistor has two depletion region over here. Let me draw in yellow color. Okay, so over here is one depletion region, and over here is also one depletion region. Okay, so the voltage from the IB and IE is not the same. Okay, and also IC and IE is not the same. IB is not the same with IE, even though you can see here from the source, the same source into the source over here, but the current flow is not the same. Why it happened? Because here you have a depletion agent, and also over here you have a depletion agent. If you remember your depletion agent for normal diode, if it is a silicon type, the depletion agent is silicon type is 0.7 volt. Okay, so if germanium is 0.3 normally. Okay, so this value is referring to the depletion agent value over here. Okay, okay, so this is the arrow for the current flow from IB to IE. However, here you know that this n-type has a lot of free electron, right? So emitter has a highly doped compared to the collector. Okay, so let me draw it here. And the p-type you have holes. This one is very lightly doped compared to the collector part and also compared to the emitter part. Okay, so where is the depletion region that is the same or equal, or the depletion region that occur in the NPN? Okay, for diode, you know the N and P has only one junction, or one. The junction is called PN junction, so only one junction, so only one depletion region. So where is this region inside the NPN transistor? Okay, you can see there are two depletion region over here and also over here. But is these two depletion region have a same value, has the same depletion region value, or the okay? So here you have emitter part, you have more carrier, right? More carrier compared to the collector part. So the carrier over here, the emitter part will emit the electron, okay, because it has more free electrons compared to collector part. So it will emit the electron over here to the holes, and also from the holes it can this free electron can move over here. Okay, so from here it can move to here. However, here this one has a lot of free electrons, so it have more energy. Okay, free electron here have more energy compared to the free electron inside the collector part. That's why the free electron in the emitter part can move to the p-type, and then it moves to the holes inside the p-type, and then it can move to the holes inside the collector part. Okay, so you see here the electron from emitter to the base. That's why the current flow from the base to emitter. Okay, so here it have VBE over here. VBE means B is positive, E is negative. And then another one is here, VCE. So here C is positive, right? C is connected to positive, E connected to negative. So when you want to label the value, example here I will write VCE. The alphabet that comes first is the positive, and then the alphabet that come later is negative. So here the value is measured from the C, from the collector to emitter. Okay, if you write VEC, it is vice versa. It means that E is positive and C is negative. Okay, so here as because the emitter part, the free electron in the emitter part is moved to the holes inside the p-type at the base. Okay, so the first depletion region can be considered as as equals to this one. Okay, if your semiconductor is silicon, so this one is considered as 0.7 volt. Okay, then how much is your VCE? So here, if you want to know your VCE, you can do the KVL. Okay, here you have positive and negative. Okay, so if you want to determine your VCE, you can do the KVL over here. Alright, so the KVL is equals to V equals to VCE, right? Because there is no resistor inside the circuit. Okay. Okay, another important current flow in this transistor is that you can see here there is this is the ground. Okay, so the current that flows to the ground is actually equals to the currents that come in. Okay, so the current that come in are this current IB and also IC. So IE is the current that goes out. So you can see here IE equals to IC plus IB, and IB is very small. Why IB is very small? Because B terminal or B region here, the P, this P is lightly doped. So it means that only at one time only a few electrons that can flow to the P type. Okay, only little maybe if this P has two holes, so at one time only 2 electrons can flow to the holes. Okay, that's why this IB is very small compared to IC and IE. Okay, right, IB is very small compared to IC. If you have NPN transistor, you know that this end is collector, this is base, this is emitter. So the current flow through IC, IB. Okay, so IB is very small compared to IC. However, IE is equals to IC plus IB. Okay, and IB is very small. So if we take into account the ratio between IC and IB, we get the current gain, which is labeled as beta. Beta equals to IC over IB. So if you have IB is around 1 microamp, and you have IC is equals to 10 milliamp. Okay, so you can determine how much is your beta, or how much is your current gain. Another value is alpha. So alpha is the short circuit current gain, or the ratio between IC and also IE. You know that IB is very small, right? Very small. So if you divide IC with IE, you will get the alpha value, or the ratio between the short circuit current gain. If you want to look further relationship between alpha and beta, you have alpha equals to IC over IE and beta equals to IC over IB. And also you know that I at the emitter part is equals to I at collector plus I at base. So if you replace this alpha and beta inside the current, this is KCL of your transistor. Okay, so you will get you will get IE equals to beta plus 1 IB, or IC equals to beta IB, right? Okay, in this subtopic, we're going to learn about DC analysis when we use BJT as an amplifier inside our circuit. So you know that this CE, CB and CC is the configuration of your BJT. So common emitter, common base, and also common collector. BJT also have a Q point. Okay, same with the diode. It has the operational point. Okay, we also can do the graphical method or mathematical method. Okay, we also can give BJT fixed bias or emitter stabilized bias, and also voltage divider, right?